Welcome, friends. So, we are dis- discussing AC network, which is three phase. So, previously, we have seen the various aspects of three phase networks and its advantages over single phase network or two phase networks. There are fundamentally two different networks available in these three phase networks. The first one we have seen, which is called star connected network or Y connected network. We have found some important results where phase voltages is related with the line voltages by a factor of √3. That means line voltage equals to √3 times phase voltage. In case of current, line current and phase current are equal. Now, total power consumed in the star connected network is √3 times line voltage into line current into power factor of the network. Also, we have seen that reactive power, total reactive power required for the star connected network, again it is √3 times line voltage into line current into sin phi. Now, in this present session, we shall discuss the second type of network, which is called delta connected network, or sometimes it is called pi connected network. So, this figure 3, it's this is the, you see, this is the delta connected network. It's looking like a triangle or delta, so that is why it is called delta connected network. We try to understand the different parameters of this delta connected network. First, this is current IR, this is IY, this is IB. So they are called respective phase currents. They are called respective phase currents. Okay, IR, IY, IB, all are equal for a balanced system. They are called phase currents. So since they are all equal, we call them as I phase, IPH. Now let us consider this node. So to this node, you see this IR current is entering, this IR current is entering like this, and IB current is leaving from that node, just like this. And additionally, one current is also there, which is called IRB. So with respect to this node, let us say this node is X. Okay. So with respect to node X, one current is entering, which is IR. One current is entering, which is IR. And two currents are leaving. So one current is IB and another current is IRB. So incoming current equals to outgoing current. That is the formula. We shall discuss more on this topic, that is incoming current and outgoing current, in the later phase of this course. We got this result from a very famous law. It's called Kirchhoff's current law, KCL. So we shall discuss more on details. Okay. So from there, what is important here is that we got IRB what is important here is that from this equation IRB is nothing but IR minus IB. IRB is nothing but IR minus IB. So similarly, we have a current IYR. So applying the same logic, IYR will be is equal to IY minus IR. And for the third current IBY, this will be IB minus IY. So these three currents, IRB, IYR and IBY, this should be I, not V. So they are all called line currents. So in short, we represent them as IL. So from this result, so these three equation, so this is 1, this is 2, this is 3. So from this three equation we can understand one thing clearly, that in case of delta circuit, line current and phase currents are not equal. What we have observed in case of a star network. So so line current must be different than a phase current in case of a delta network. So now we try to understand the phasor diagram of different current phasors. So let us say this is IR. This is IR phasor, this phasor, this red phasor IR. Then we have IY phasor 120 degree lagging. Then we have IY phasor, it is IY phasor. This is 120 degree lagging. This angle is 120 degree. And finally we have IB phasor. It is directed along this direction. This is IB. So these three phasors are separated by an angle of 120 degree. Okay. So now from the first equation we can see that here it is IR minus IB, here IR minus IB. So just like we have seen in case of a phasor diagram, in case of star network, there that IB should be negative. So IB, that means B phase should be negative. So this is the minus IB. This is the minus IB in this direction. This is minus IB. So phasor summation of IR and minus IB. Phasor summation of IR and minus IB. So phasor summation of IR and minus IB will be IRB, will be IRB. It is represented by this phasor IRB. Similarly, for IYR, and IYR is equal to IY minus IR. So IR should be taken negative, in negative direction. IR should be taken in the negative direction. So if this is IR, then it should be minus IR in this direction. This is minus IR. So the phasor summation of IY and IR, it will be giving the phasor summation of IR and IY, or IY and minus IR will be this phasor, which is equal to IYR. And same logic, we can get a similar phasor representation of I Py. So with respect to each line phasors, that is also 120 degree phase displaced with respect to each other. So now if you want to calculate the relation between IRB with respect to IR and IB, so we follow the parallelogram law. So it is from this diagram, if the angle between IR and minus IB is equal to 60 degree, this angle is 60 degree. So we write, it is the formula is just we have mentioned, if two vectors is connected in this fashion by making an angle of theta, then resultant vector R should be given by resultant vector, it is p square plus q square minus 2pq cos theta, then whole under root. So first term is IR square, second term is minus IB square, then minus 2 IR into IB, and lastly we have cos 60. So if you substitute this value, IR minus IB all are phase quantities, so they are substituted by I phase, which is phase current, and if you substitute cos 60 equal to half, we get a relation is root 3 times I phase. So we get a relation, a very important relation or similar relation is that line current becomes root 3 times phase current. Line current becomes root 3 times phase current, which is this relation we obtained for star connected network for voltage phasors, but in case of a delta connected network we obtain this relation in case of a current phasor. Now if you look, what about the voltage phasors? So let us say again, this is the load according to the figure 2. This is R phase, this is Y phase, and this is P phase. Now if this represents R phase only, so voltage appearing across R phase is only VR. So let us say this represents R phase, okay? Let us say this represents only R phase. So voltage appearing across R phase is VR. So it is phase voltage is VR. Now whatever voltage is appearing, now this voltage, you see the voltage appearing across between R and Y, VR and Y. So from the diagram itself it is quite clear that VRY is equal to VR. VRY is equal to VR because they are connected such a fashion which appears as a parallel. So that is why this VR becomes VRY. So VRY stands for line voltage and VR stands for phase voltage. So that is the reason we get this relation of voltage is equal to line voltage is equal to phase voltage for delta connected network. So we get, if you compare these two network, one is star connected network and another one is got delta connected network. So in case of star connected network, we have VL, that is line voltage, that is becoming root 3 times phase voltage. But in case of a delta connected network, we have line voltage is equal to phase voltage. we have line voltage is equal to phase voltage. However, in case of a current line for star system, we have line current is equal to phase current. However, in case of a delta connected network, line current it is root 3 times phase current. Now let us coming to the power. So total power, that is the total power can be evaluated at, what is total power? Power consumed at each phase. At each phase, that is summation. That is the summation of power consumed at each phase. So the first term, it is the power consumed in R phase. The second term, power consumed in Y phase. Third term, power consumed in B phase. So summation of all these powers gives you the total power. So the summation of R phase is equal to VRY into IR cos phi. Similarly, Y phase VYB into IY cos phi. Similarly, B phase VBR into IB cos phi. So you know this VRY is the line voltage, VYB also line voltage, and VBR also line voltage. So 3 VL will coming, and since for the delta connected network VL is equal to V phase, so we write here 3 V phase. And similarly, IR, IY, IB all are phase current, so we write I phase. And with that we have a power factor. Now 3 V phase, this 3 V phase, I phase into cos phi. So that becomes 3 into, now V phase is equal to line voltage by root 3. I phase becomes, sorry, it is for the delta connected network. V phase becomes V line. I phase becomes, that is phase current becomes line current by root 3 into cos phi. So altogether we getting root 3 VL IL cos phi. So total power consumed in delta connected network is root 3 VL IL cos phi. So in case of a star connected network and delta connected network, total power is same. Which is P is equal to root 3 VL IL cos phi. And similarly for reactive power we get the similar relation, but instead of cos phi we have sin phi. So total reactive power Q, which is same for both the connection, star connection and delta connection, Q is equal to root 3 times VL IL. Now this time it is sin phi. So let us quickly recap what we have gone through. So first we have understood this IR, IY, IB are the 3 phase currents. We call them as I phase. Then we have understood that IRY, IYB, IBR, they are called line currents, they are called I line. Now respective line currents lags by 30 degree than its respective phase currents. It's very true, as we can, so you see this is IRB, okay. So this phasor is IRB. Let me erase. So let us say this phasor is IRB. And this phasor is IR. So this angle is 30 degree. So respective line currents here, line currents IRB is lagging by an angle of minus 30 degree. It is lagging by an angle of lags by 30 degree then respective phase current, which is IR. So which is also true. Now we have also derived line current becomes root 3 times phase current. We have also observed that line voltage is equal to phase voltage in case of a delta connected network. And what is our power? Active power is root 3 times line voltage into line current into cos phi, and reactive power we have the same relation but we require sin phi instead of cos phi. So we have understood both the network, star connected network and delta connected network. Voltages and current relations are opposite. In case of a star connected network, line voltage is root 3 times phase voltage, but in case of a delta connected network they are all same. When it comes to current becomes same, all line current and phase current become same in case of star connected network, and in case of a delta connected network line current becomes root 3 times phase current. So I am ending right now with this background knowledge, background theory. We shall see some numerical demonstration in the next session of this course. Thank you.